Let's talk about capacitors and direct current. Capacitors are part of almost every electronic device out there, but what exactly are they? How do they work? And how do they affect the direct current network? A simple capacitor comprises two conductive plates and a layer of dielectric. When in use, one plate is negatively charged, it is then called anode, and the other positively charged, called cathode. But usually, capacitors don't look like two plates because they have many layers of those plates packed together. When connected to a circuit, electrons will be taken out the anode and added to the cathode. This will create an electric field in the space between the plates. The dielectric made of insulating materials reduces this electric field and allows the capacitor to store more energy, effectively increasing its capacitance. The equation to calculate this capacitance is the permittivity of space times the relative permittivity of the dielectric, which is 1 if it's vacuum, times the area of the plate and divided by the distance between them. Sum of the capacitance of capacitors connected in parallel simply is the algebraic sum of their values, while that of those in series is the inverse of the sum of the inverse. For example, with three capacitors of 2, 4, and 5 microfarad, their parallel sum is 11 microfarad and their series sum is just over 1 microfarad. Now, how do these capacitors affect the DC network? A DC network is one where the current moves in one direction and the voltage does not change its sign. You should take note of this time constant equation. In this network, during the charge phase, the capacitor will store energy until its voltage is equal to the source and the current through it equal effectively zero, which is after about 5 time constants. When the power source is shorted, the capacitor enters its discharge phase. After 5 time constants, its voltage returns to near zero and its current, flowing in the opposite direction, starts at the maximum negative and eventually becomes zero. Now, with all the formulae available, let's try solving the example. If the source voltage is 10 volts, the resistance is 4 kilo ohms and the capacitance is microfarads, the time constant will be 20 microseconds. That means after 140 microseconds, the current through C will be about 2.28 microamps, which is effectively zero, and the voltage across it is 9.99 volts, which is about that of the source. And after 100 microsecond discharge, the current will be minus 16.8 microamps, and the voltage decreases to just over 67 microvolts. That's the end of the video. Thank you for your attention.